rich material. We want to help you become truly well-informed on how machine learning is being applied right now to solve those complex challenges across so many diverse engineering fields. We'll explore surprising facts, maybe uncover some cross-disciplinary connections, and illustrate ML's immense potential. Hopefully give you those aha moments that really stick. When we talk about engineering, our minds often jump to, big things, bridges, cars, jet engines.
The usual suspect.
Right. But machine learning is profoundly reshaping something even more personal, more intimate, our health and well-being. It's truly shifting how we approach disease, moving from just sort of reactively curing illness to actively managing health across an entire lifespan.
It's a massive shift.
Imagine a world where your health isn't just reacted to when something goes wrong, but it's proactively guided, monitored, optimized by these intelligent systems. That's the paradigm shift ML is bringing, isn't it?
It absolutely is. And what's truly fascinating here isn't just the sheer breadth of ML's impact in healthcare. It's that fundamental change it represents. It's playing key roles in detecting diseases with, frankly, unprecedented precision, and at much earlier stages, too. That improves diagnosis vastly, helps develop better, more personalized therapies.
And it's not just the big hospital machines, right? You mentioned integrating data from our lives.
Exactly. That's a key point. It's about integrating data from all aspects of our lives to create this holistic, continuous view of health. It makes health management an ongoing, dynamic process rather than just, those episodic interventions when you go see the doctor.
And it goes way beyond the clinic then. This whole concept of smart healthcare is really taking hold in our homes, in our daily lives. It's moving care out of the traditional doctor's office.
Precisely. ML techniques are advancing disease detection, monitoring compliance with treatment plans, are you actually taking your meds, and even tracking a patient's response to therapy, all directly in their homes.
How does that work in practice?
Well, think about it. We're seeing data collected from everyday devices you already own. Your smartphone, maybe smart home assistants like Google Home or Amazon Echo, and increasingly specialized wearables.
Right, like fitness trackers, but more medical focused.
Exactly. These digital tools contribute to this continuous, rich stream of information. And that allows for more advanced ML applications in everything from, say, remote health monitoring to developing preventative care strategies. And within hospitals, too, ML empowers healthcare providers to diagnose more accurately, to personalize care for patients, even as those patients move between different settings, ER to inpatient to rehab.
So it ensures continuity.
It does. It ensures continuity and really tailors treatment to the individual's evolving needs.
That's powerful. But, okay, with all this incredibly sensitive health data flowing around from our phones, our smart devices, hospital records, privacy must be a massive concern. Maybe the massive concern.
Oh, absolutely.
How do we collect and analyze it to improve health outcomes without compromising individual patient information? This seems like a real tightrope walk.
It is more than a concern. It's a critical challenge. But it's also where ML offers truly innovative solutions. In medical applications, where health data is protected by strict regulations, KTTA, pay, and so on, and it's inherently highly sensitive, ML techniques like federated learning are absolutely crucial.
Okay, federated learning. What's the elevator pitch for that?
Right. So imagine you have data spread across many different locations, multiple hospitals, maybe research centers, or even individual patient devices, potentially. Instead of gathering all that raw, sensitive data into one central database, which, is huge privacy risk.
Well, a huge target.
A huge target, exactly. Federated learning allows the ML model to go to the data. The model is sent out to each location, it learns from the local data right there on site, and then only the learned insights, the patterns, the updates, not the raw data itself, are sent back to a central server to update the global model.
So the raw data never leaves its secure location.
Precisely. This method thereby preserves individual patient privacy by never exposing their raw data, while still allowing the aggregate knowledge to improve the ML models for everyone. It's a fundamental shift in how we approach data collaboration in sensitive fields.
That's clever. Very elegant.
It is. However, despite these advancements, we still face challenges. The existing medical literature, for all its volume, often contains unstructured data, metadata that can be incomplete or inaccurate.
Right, like handwritten notes or inconsistent formats.
Exactly. And this makes it difficult for ML models to generate meaningful relations or derive robust insights without significant, sometimes very difficult, pre-processing.
Okay, that makes sense. So assuming we can manage the privacy with things like federated learning, if ML is monitoring us and learning across these distributed data sets, how does it bring that precision you mentioned to critical early diagnoses like in cancer detection? This seems like a perfect place for ML to really shine, given the stakes.
This is precisely where specific supervised learning algorithms demonstrate their immense value. Take breast cancer classification, for example, a classic but critical application. Here, ML models are trained to classify cancer from detailed patient data, making predictions far more efficient and, importantly, accurate than traditional, often subjective, diagnostic methods.
More consistent, too, I'd imagine. Less dependent on individual interpretation.
Exactly. The real insight isn't just about speed, it's about reducing the chance of human error and providing consistent, data-driven assessments.
Can you walk us through some of the specifics there? What kind of data are we actually talking about, and how do these algorithms work to get that level of precision?
Certainly. In one study detailing the source material, researchers extracted data from images of cancer cells from 570 patients. Not a trivial number. They used 30 distinct attributes or features to classify the cancer. These features describe characteristics of the cell nuclei from a digitized image, one obtained via fine needle aspirate, or FNA.
Okay, so what are these features, like size and shape?
Exactly. Imagine these 30 measurements, detailing everything from the cell's radius, texture, perimeter, and area, to its smoothness, compactness, concavity, concave points, symmetry, and even its fractal dimension.
Wow, that's detailed.
It provides the ML model with a very comprehensive quantitative profile of each cell.
So it's about identifying incredibly subtle patterns in these characteristics, things that might be invisible or just too complex for the human eye alone.
Precisely. And a crucial early step involves identifying key correlated features. You don't want redundant information confusing the model. For instance, they used a heat map visualization, a common technique which showed that radius mean, perimeter mean, and area mean were highly correlated. Makes sense, right? Bigger radius often means bigger perimeter and area. And similarly, concave points mean, concavity mean, and compactness mean were also strongly linked. This process is vital because it helps in selecting only the most relevant features for analysis. It prevents the model from being overwhelmed by redundant or noisy information and focuses its learning on what truly differentiates between cancerous and non-cancerous cells.
Streamlining the input.
Exactly. Once these refined, relevant features are selected, common supervised learning algorithms are applied. You hear these names a lot. K-nearest neighbors, KNN.
Right, classifying based on similar examples.
Yep. Then decision trees, making those if-then decisions. Logistic regression, which is a statistical model for binary outcomes, cancer, no cancer, support vector machines, or SVMs, which find the optimal boundary between classes.
That sounds powerful.
It can be. And random forest, which is essentially an ensemble like a committee of many decision trees voting together. Each has its strengths, but they all learn from labeled data where we know the outcome, to make predictions on new, unseen data.
And cleaning the data is key before you start.
Oh, absolutely vital. Before any of these algorithms can do their best work, data pre-processing is critical. This involves meticulously cleaning the data, filling any missing values. You can't have gaps removing outliers that could skew the results, and critically standardizing the data.
Standardizing, what does that mean exactly?
It means ensuring that all features are scaled to a comparable range, maybe from -1 to 1 or 0 to 1. This prevents features with naturally larger numerical values, like area perhaps, from disproportionately influencing the model's learning compared to features with smaller values, like maybe a tester score. It allows for a more balanced and accurate analysis.
Okay, that makes perfect sense. That's incredible precision for early diagnosis.
Right.
So from there, ML is now moving into predicting patient outcomes, you mentioned.
Yes, that's a huge area.
Myocardial infarction or heart attack?
Yeah.
That's a serious concern, and its outcomes are notoriously difficult to predict, aren't they? How does ML help here, especially when the factors are so numerous and complex? It must be incredibly challenging for humans to predict.
It really is. Myocardial infarction is often tragically called a silent killer, precisely because of its hard-to-predict outcomes. These outcomes are influenced by this dizzying multitude of interconnected factors: diabetes, high blood pressure, cholesterol levels, smoking history, family history, lifestyle choices. The list goes on.
It's not just one thing.
Not at all. The complexity comes not just from the number of variables, but their intricate interactions and the sheer volume and variety of data involved. Data sets can be enormous, We're talking up to 111 input parameters detailing a patient's entire medical profile, potentially, and maybe 12 potential outcome attributes or complications that might arise after the event.
Wow. 111 inputs.
Yeah. Traditional medical models, even expert human intuition, really struggle with that scale and interconnectedness.
So what was the research gap that ML stepped in to fill here, and how did it overcome those difficulties? The missing data you mentioned earlier, the complexity.
Right. A significant research gap was identified in dealing with this large number of input attributes, coupled with those common real-world issues like missing values about 7.6% in one data set discussed, which is substantial, and also the long training times required for traditional complex models. To overcome these challenges, researchers found that neural decision forests, or NDFs, are particularly effective.
Neural decision forests. That sounds like a hybrid approach.
It is. It ingeniously combines convolutional neural networks, CNNs, and random forests. Think of it this way. CNNs are excellent at automatically extracting hierarchical features and patterns from raw data, like how they identify edges, then shapes, then objects in an image. They do something similar with complex medical data, finding subtle, nonlinear relationships.
Okay, so the deep learning pattern recognition part.
Exactly. They bring that power of deep learning. Random forests, on the other hand, are highly robust for classification tasks, leveraging that ensemble of many individual decision trees. So an NDF consists of many interconnected decision trees where each tree makes a prediction, and then the average or the vote of these predictions is taken as the final output.
Best of both worlds, maybe.
Kind of. This ensemble approach leverages the strengths of both. Neural networks for complex pattern recognition and decision trees for robust, often more interpretable classification. It creates a much more resilient and accurate predictive model overall.
That sounds really powerful. What kind of data did they actually use to test this, and how well did it perform in predicting those critical outcomes? Did it make a real difference?
It did. A compelling case study utilized the well-known UCI machine learning MI complications dataset. This dataset is quite comprehensive. It contains 1,700 instances, each representing a patient, and 124 unique attributes. That breaks down into one attribute for patient ID, 111 for those input parameters, clinical measurements, risk factors, etc., and 12 for the predicted outcomes or complications.
What kind of complications?
Things like fibropreds, fibrillation predictions, pred-sta, tachycardia predictions, gelota, ventricular tachycardia,
Yeah.
and lettuce, lethal ischemia, among others. Really serious potential outcomes.
Definitely critical. And the performance?
When trained with specific parameters, for instance, a batch size of 100, 10 epochs, which passes through the data, a tree depth of 5, and randomly selecting 50% of the input features for each tree, which helps robustness, the NDFs showed really superior accuracy. For example, in predicting pred-sta, one of those specific cardiac complications, the NDF achieved an impressive 98.24% accuracy.
98%. That's very high.
It is. And this significantly outperformed a single neural decision tree in several categories. For instance, predicting otic-lance, another complication, saw accuracy improve dramatically from just 61.76% with a single tree to an astounding 85.59% with the NDF.
That's a truly remarkable leap in accuracy. It fundamentally changes the game, doesn't it?
It really does.
The true insight here isn't just that ML is more accurate, though that's huge, but that it shifts the entire paradigm of patient care. It's moving us from that reactive, wait until symptoms appear model to a proactive predict and prevent system.
That's the goal.
This means ML can empower individuals and healthcare providers with advanced warnings, personalized insights, moving from reactive treatment to truly proactive health management. For doctors, it's almost like having a highly intelligent co-pilot, right?
Yeah.
Enhancing human capability.
That's a good analogy. It augments their expertise.
Makes you wonder what this means for the future of medical training itself. Okay, moving from our incredibly personal health, let's broaden the scope. Let's look at how ML impacts the larger, broader systems around us, our infrastructure and our environment. Things like natural disasters, floods, for example, and complex logistics, especially in areas like aviation. These are major challenges for any society.
Yeah.
Huge economic and human costs involved.
Absolutely. And it's in these large-scale dynamic environments that ML is truly making a profound difference.
Bringing a new level of
Oh, yeah.
preparedness.
Precisely. ML offers powerful, frankly, indispensable tools to anticipate, mitigate, and respond to these large-scale environmental and infrastructural risks. It brings a new level of preparedness, efficiency, and importantly, safety. Its ability to process these vast amounts of disparate data satellite imagery, sensor readings, historical patterns, and identify subtle emergent patterns. Well, it's a game changer for managing these complex systems, where traditional methods often just fall short.
Okay, let's take floods. They cause devastation across the globe every single year. Predicting them accurately has always been an immense challenge. How is ML making a difference here? How does it let us move beyond just reacting after the fact?
Well, by analyzing land use and land cover, or LULC, patterns.
Okay, what does that mean? Like forests versus cities?
Exactly. LULC patterns are themselves influenced by this complex interplay of socioeconomic factors. Think urban development, deforestation, and natural factors like soil type and climate. ML helps predict floods by understanding how these patterns affect water runoff and absorption, with significantly greater accuracy and lead time than before. Traditional methods were often slow, very labor-intensive, prone to inaccuracies. It made effective proactive measures really difficult.
Right.
But now, with advancements in satellite remote sensing and geographical information systems, GIS, tools like QGIS, we can gather and process vast amounts of geospatial data much more effectively and quickly. And we can feed it directly into these ML models.
So, what are the primary factors these ML models are considering for flood prediction? It can't just be rainfall amounts, right?
No, it's much more holistic. The models account for several key factors. High rainfall intensity and duration, obviously, that's crucial. But also, critically, the low absorption rates of the ground, which can be exacerbated by urbanization, lots of concrete and asphalt.
Less place for the water to go.
Exactly. Rising sea levels, particularly in coastal areas, naturally play a role. Inadequate or aging sewage and drainage systems in cities are a big factor too. And, crucially, low soil absorption capability, which is affected by soil composition and how much vegetation cover there is. The data sources are incredibly rich and multidisciplinary. High-definition satellite images are integrated with socioeconomic data to understand population density, where people actually live, and their vulnerability.
So you know who's at risk.
Precisely. Specific examples from the source material include using LNS-3 satellite images, particularly band 5, which uses shortwave infrared sensing. That's excellent for differentiating between water, land, and vegetation. They also use normalized difference water index, or NDWI values, which specifically highlight water bodies. These are then combined with historical and real-time rainfall data. This multi-source data integration is absolutely crucial for building a comprehensive picture of flood vulnerability.
Okay, that's a lot of data. And what kind of model processes all this dynamic multi-source information to actually make a prediction?
For prediction, the Markov model is frequently employed in these studies.
The Markov model, how does that work in simple terms?
Okay, in essence, a Markov model is like predicting the next move in a game based only on the current state you're in, not the entire history of how you got there. It assumes the future depends only on the present. It's a stochastic, meaning probabilistic, state-based transition model. It operates with a fixed number of states, typically 2 in this context for floods, being in flood what's called state A and not being in flood state B. The model calculates transition probabilities based on the observed data. So what's the likelihood of moving from not flooded to flooded given the current rainfall, soil saturation, LULC patterns?
So it forecasts the chance of switching states.
Exactly. It allows it to forecast future flood conditions with a certain probability. In one case study they detailed, a specific study area was analyzed over 5 years, 2011 to 2015. They used QGIS software to meticulously calculate those NDWI values and integrate all the available rainfall data. This kind of robust ML-driven modeling helps governments formulate proactive policies for disaster risk reduction, plan infrastructure improvements like better drainage, and crucially enables more timely and effective emergency response strategies. It can potentially save lives and certainly mitigate economic damage.
That kind of predictive power isn't just for natural disasters, then. It extends to our crucial transportation networks, where precision and foresight are absolutely paramount. And here's where it gets really interesting, I think. Air travel. Weather conditions, especially low visibility due to fog, can cause massive disruptions. We've all experienced flight delays, reroutes, and in severe cases, it can even lead to accidents. How does ML help pilots and air traffic controllers prepare for these kinds of challenges, especially when weather is so notoriously fickle and localized?
Right, weather prediction is hard. But time series data mining, TSDM, is perfectly suited for this kind of problem. Unlike static data analysis, TSDM specifically focuses on data points indexed in time. Think of it like analyzing a continuous stream of sensor readings from an airport visibility sensors, temperature, humidity, wind speed, pressure, all changing second by second.
Looking for patterns over time.
Exactly. TSDM allows us to analyze these evolving patterns over time. We can detect anomalies, classify situations, segment periods like this is a developing fog event, and most critically for aviation, make predictions about future conditions. For aviation, anticipating phenomena like fog or severe convective situations, thunderstorms, basically can vastly improve safety and efficiency
How so?
by allowing for proactive measures. Adjusting flight schedules ahead of time, rerouting aircraft before they hit the bad weather, pre-positioning ground crews and de-icing equipment, optimizing runway usage. The ability to forecast this with confidence provides invaluable lead time.
Okay, let's get specific. How does this work for something as seemingly unpredictable as fog forming around an airport?
Well, the problem is that fog formation is the most common meteorological phenomenon reducing visibility. It leads to those delays, disruptions, and sometimes worse. The runway visual range, or RVR, is the most critical variable here. That's the distance a pilot can actually see markings or lights on the runway. Research is focused specifically on predicting RVR using various sensor data, aiming for a practical 6-hour time horizon, enough time to make decisions. They define fog events specifically as RVR falling below 1990 meters, which effectively turns this into a binary classification problem. Predict fog or no fog in the next 6 hours.
Simple output, complex prediction. Was there a specific case study that showed this actually working, a real-world validation?
Yes, a compelling case study at Valladolid Airport in Spain focused precisely on this fog prediction problem. Researchers there developed a multi-objective evolutionary algorithm, MOEA, to train artificial neural networks, ANNs.
Okay, unpack that a bit. ANNs are the brain-inspired models. What's the MOE8 part?
Right. ANNs are great at learning complex nonlinear relationships in data. MOEAs are optimization techniques. They help fine-tune the ANN structure and parameters to achieve multiple goals simultaneously. In this case, maybe maximizing the accuracy of predicting fog, while also minimizing false alarms, and perhaps keeping the model relatively simple.
Finding the best trade-off.
Exactly.
Right.
And the best model they developed achieved a global accuracy of 82.24%. Pretty good. But even better, it correctly classified 84.83% of the actual fog events, high sensitivity to the dangerous condition.
That's impressive.
What's even more compelling, especially for aviation safety, is that the resulting model was highly interpretable. It used only 2 neurons in its hidden layer, which is very simple for an ANN. This meant its output, its predictions, could actually be explained in terms of the underlying physical properties of fog formation. That gives meteorologists and air traffic controllers confidence in its predictions, which is absolutely vital in critical safety systems.
Yeah.
You need to trust a black box.
That's truly remarkable, especially that interpretability aspect. That's often a criticism of complex ML models, isn't it? The black box problem.
It is, so achieving interpretability here is a big win.
And what about more severe weather? Predicting thunderstorms, which can be even more dangerous for flights than fog.
Yes, the research also tackled the prediction of convective situations, specifically classifying different types of convective clouds: clear skies, cumulus congestus, TCU, the towering ones, cumulonimbus, CB, the real thunderstorm clouds, and active thunderstorms, TS. This was done with a longer 12-hour forecast horizon, based on a different set of atmospheric variables and stability indices, this time at Madrid-Barajas Airport. In this case, hybrid ANNs were found to be an excellent approach, particularly useful for imbalanced data sets.
Imbalanced, meaning?
Meaning clear weather patterns are obviously much more frequent than rare, but severe thunderstorm patterns in the training data. Hybrid ANNs can be designed to give more weight or attention to these rare but critical events so they don't get overlooked.
Makes sense. You want to be sure you catch the dangerous stuff.
Absolutely. And the overall benefit of these ML applications is profound. They lead to significant improvements in the safety and the profitability of aviation operations, reducing delays, enhancing resource allocation, and most importantly, providing that critical lead time to prevent accidents.
So whether it's managing a flood with more foresight or landing a plane safely through challenging weather, ML is providing this proactive layer of intelligence. It's helping us manage complex systems that directly impact our daily lives and our critical infrastructure. It really is about knowing what's coming before it arrives. That changes everything. So what does all this mean for the advanced technologies we're increasingly relying on day in and day out? I'm thinking, electric vehicles showing up in more garages, the lightning fast 5G networks connecting us. It seems like ML is not just a feature anymore, it's becoming the core intelligence. It allows these systems to manage their own immense complexity. It's like the silent conductor of our increasingly smart world.
Absolutely. That's a great way to put it. These modern systems generate vast, almost unimaginable amounts of data, and machine learning is fast becoming the only way to process it efficiently. And this isn't just to boost raw performance, though it certainly does that. It's also essential to navigate increasingly critical issues like user experience, reliability, and crucially, privacy. These are paramount in today's hyper-connected world.
Right.
Without ML, frankly, these technologies would simply buckle under their own data weight. They'd be too complex to function effectively.
Okay, let's talk EVs. Battery performance can make or break the electric vehicle experience, can't it? It dictates range, charging time, overall lifespan. This has traditionally been a major bottleneck for EV adoption. How is AI or ML supercharging this critical area, pushing the boundaries of what's possible?
ML is absolutely vital for the EV revolution. Think of it as a hyper-efficient R&D assistant. In battery testing and development, engineers traditionally have to try this massive number of permutations, different materials, cell designs, charging protocols. It takes forever.
Trial and error, basically.
A lot of it, yes. But AI, particularly research coming out of leading institutions like Stanford and MIT, is now able to quickly identify the most promising approaches among millions of possibilities. We're talking about cutting testing and development times by up to an astonishing 98%.
98%, that's incredible.
It is. Imagine the acceleration and innovation that enables, bringing next-generation batteries to market in months instead of years. Designing ultra-fast charging batteries, for example, is a major challenge because charging too intensely often causes early failure and degradation. ML helps optimize these charging methods, finding that sweet spot, balancing speed with longevity, and that's critical because battery packs represent such a significant portion, often over a third of an EV's total cost. Making them last longer and charge faster is key.
That's an incredible acceleration in R&D. What about the charging infrastructure itself? That's often cited as another key barrier to widespread EV adoption, right? Range anxiety, finding a working charger.
Definitely. And AI and ML are also transforming how we understand and improve the charging infrastructure. They're analyzing streaming data from, get this, over 12,720 EV charging stations and concurrently processing 12,720 user reviews across 651 U.S. core-based statistical areas.
That's a mountain of data.
It is. And ML reduces the processing time for insights from potentially weeks for human experts who would have to laboriously comb through all that data down to mere minutes of computation. It offers near real-time insights into infrastructure performance and, critically, the actual user experience.
And what did they find? Anything surprising?
Yes, something truly surprising and even a bit counterintuitive came out of that analysis. Contrary to what you might predict theoretically, the analysis found that charging stations at private locations, maybe workplaces or apartment complexes, did not consistently outperform public charging locations in terms of user satisfaction.
Really? You'd think private ones would be better maintained or less crowded.
You would think. And even more startling, nearly half of drivers using mobility applications to find and use chargers reported negative experiences overall.
Half. That's not good.
Not good at all. And this isn't just a statistic, it's a profound insight. It challenges the common assumption that private controlled environments would inherently lead to better user experiences. It suggests that the user interface, the reliability, the maintenance standards of the charging infrastructure itself, regardless of who owns it, are the critical bottlenecks.
So it's not just about location, it's about the whole experience.
Exactly. For engineers designing future infrastructure, this is a clear call to action, focused not just on installing more chargers, but on the entire digital and physical user journey, from finding the charger to plugging in to payment to reliability. It all matters.
That's a fascinating and honestly somewhat unexpected insight. What about managing the batteries once they're actually in the car, optimizing their performance over years of use?
Right, the battery management system, or BMS. For lithium-ion, batteries, which are inherently complex, nonlinear, time-variant systems, AI-based BMS, are becoming crucial. They're predicting critical states like state of charge, so it's basically how much energy has left your fuel gauge, state of health, so how degraded the battery is compared to its original capacity over time, and remaining useful life, RUL, how much longer the battery can reliably function before needing replacement.
So it's like a health checkup and a lifespan prediction for the battery.
Precisely. This predictive intelligence extends battery life by optimizing charging and discharging, enhances safety by anticipating potential failures before they happen, and optimizes performance throughout the vehicle's lifetime. And to implement this AI effectively, right there in the BMS inside the car, hardware accelerators like FPGAs, field programmable gate arrays, are proving crucial.
The customizable chips, right?
Exactly. Think of an FPGA as a highly customizable chip that can be rewired, reprogrammed on the fly to perform very specific, repetitive, parallel tasks extremely efficiently. Unlike a general-purpose CPU or GPU, this makes them incredibly good for the demanding, high-speed computations ML requires in real-time embedded systems like a BMS, and they often use significantly less power than a standard processor, which is obviously vital in a battery-powered device like an EV.
Makes sense. So these intelligent systems aren't just making our vehicles smarter, they're becoming foundational to our entire communication backbone as well. Which brings us neatly to 5G. This technology promises, ultra-low latency, incredibly high data rates. It's positioned as the nervous system of our modern world. But with potentially billions of diverse devices connected everything from smart factory robots to critical medical implants, how on earth do we manage such immense complexity? What role does AI play in making this game-changing technology actually work?
5G is indeed incredibly complex. It's characterized by extreme heterogeneity, meaning wildly different types of devices needing different kinds of service, and just massive device connectivity, far, far exceeding previous generations like 4G. AI and ML aren't just helpful additions here. They're widely considered game-evolving technologies for 5G. They provide the adaptability, the intelligence, the autonomous management needed to meet these really ambitious demands.
So without AI, 5G basically wouldn't work as promised.
It would be incredibly difficult, if not impossible, to manage effectively at scale. Without AI, the sheer scale and the dynamic nature of a 5G network would simply be unmanageable by human operators alone. It would be like trying to manually direct every single car on every road in a major city simultaneously during rush hour. Just not feasible.
Okay, so how exactly is AI being woven into the very fabric of 5G? What's it doing to make it smarter and more robust?
There are several key, absolutely indispensable applications of AI and ML in 5G. First, network optimization. ML algorithms process vast amounts of cross-domain data, geographic info, engineering parameters, real-time traffic patterns to accurately estimate peak traffic demands in different areas. This allows for dynamic optimization of capacity expansion, intelligent coverage adjustments in real-time boosting signals where needed, and just much more efficient resource allocation overall.
Making the network adapt on the fly.
Exactly. Second, cybersecurity. This paramount with the proliferation of all those Internet of Things, or IoT, devices connecting via 5G. It creates a massive potential attack surface. AML identifies suspicious activities by analyzing network traffic patterns and device behaviors, classifying new threats, and helping with authentication, validation, and preventing advanced, evolving attacks, things like confusion attacks, polymorphism, pantomime attacks, which are specifically designed to evade traditional signature-based defenses.
So it's learning to spot new threats.
Essentially, yes. Third, energy efficiency. This is a major global concern. Information and communication technology, ICT, consumes a significant amount of energy. AML can help build intelligent wireless networks that proactively predict traffic load and user mobility patterns. This allows the network to dynamically power down or even completely shut down parts of the radio access networks. I ran the cell towers, basically during periods of low traffic, leading to substantial energy savings without impacting user experience.
Smart power saving.
Very smart. And finally, ML optimizes network slicing.
Network slicing.
Think of it like creating dedicated virtual lanes on the 5G highway for different types of traffic. One slice might be optimized for ultra-reliable, low-latency communication needed for, say, remote surgery or factory automation. Another slice could be for high-bandwidth mobile broadband, like streaming video. A third might be for low-power, massive IoT deployments. ML helps manage the allocation of resources to these different slices dynamically based on demand. And it also helps with caching. By predicting what content users in a certain area might request soon, maybe a popular video or software update, and storing it closer to them in the network edge, which reduces latency and backbone traffic.
Yeah.
All these intelligent layers make the network far more efficient and responsive.
The requirements for 5G sound incredibly ambitious, far beyond what 4G delivered. Are these even achievable without AI, or is AI truly the linchpin holding it all together?
They are indeed ambitious, almost revolutionary targets. And yes, AML is absolutely critical to achieving them. Just to recap some numbers, 5G aims for 1 to 10 gigabits per second speeds, maybe even higher eventually. A mere 1 millisecond latency for real-time applications, 1,000 times the bandwidth or unit area compared to 4G,
Yeah.
supporting 10 to 100 times more connected devices.
Wow.
And on top of that, targeting 99.9999% availability, the 5.9's reliability, meaning virtually always on, plus a 90% reduction in network energy use compared to 4G levels, and extending battery life for low-power machine-type devices up to 10 years potentially.
Those are staggering numbers.
They are. And these targets define a level of performance, efficiency, and reliability that simply cannot be met with traditional static network management approaches. AI and ML provide the necessary intelligence to dynamically adapt, optimize, self-heal, and secure these hyper-connected, high-performance networks in real time. It's the only way to manage such a complex living system effectively.
Okay. So as more and more data inevitably flows through these intelligent networks and systems, the question of privacy becomes even more paramount, doesn't it?
It really does.
All these incredible applications generate vast amounts of data, but sharing data, especially sensitive information like the medical records we talked about, or maybe financial transactions, location history creates this huge privacy challenge. How can ML help here beyond just securing the network from external hackers? This feels like it moves us into a really nuanced ethical and practical dilemma about the data itself.
You're absolutely right. This is a truly critical area, and it moves us beyond basic cybersecurity into that fundamental dilemma: data utility versus individual privacy. Organizations like health sectors, pharmaceutical companies, government agencies, they often need to share data with researchers, other agencies, or third parties for various kinds of analysis. Maybe it's for public health studies, drug development, policy making, lots of legitimate reasons.
But they can't just hand over raw data.
Exactly. They must do so without disclosing individual sensitive information. The challenge is balancing that privacy preservation, the individual's right to control their data, with maintaining data utility, meaning the data has to remain useful and statistically meaningful for the intended analysis.
It's an incredibly tough tightrope walk because too much privacy protection, too much anonymization can render the data useless, right? But too little can lead to devastating privacy breaches.
Precisely. It's a fine line.
So what's the core problem they're trying to solve here, especially when traditional methods fall short?
A major issue arises with what's often called the 1IM dataset problem. One to many.
One to many.
Yes. In many real-world scenarios, a single individual might have multiple records associated with them, potentially containing different sensitive attributes over time. Think back to the cancer patient example. They might visit various doctors, undergo multiple treatments, fill different prescriptions over several years, leading to many records, perhaps spread across different databases or different time points within one database.
Why? It's not just one neat row per person.
Exactly. Traditional 1.1 privacy models, which often implicitly assume one single record per individual, frequently fail in these complex 1RM scenarios. It becomes much easier for someone to potentially link seemingly anonymized data back to a specific individual, leading to serious privacy breaches. And the problem is further complicated by the different types of information we need to handle. We have explicit identifiers, the obvious ones, like name, social security number, maybe a specific patient ID. Those need to be removed or strongly protected. Then there are quasi-identifiers. These are attributes that seem non-sensitive on their own, like sex, age range, zip code, maybe date of admission. But when you combine several of them, perhaps with external public sources like voter registries or online profiles, they can potentially uniquely identify an individual.
The re-identification risk.
Yes, exactly. And finally, you have the sensitive attributes. This is the truly private information we want to protect, like the specific disease diagnosis, medications, income level, political affiliation, things like that. The goal is to protect these sensitive attributes while allowing the quasi-identifiers to still be useful for analysis, but in a generalized, safe way.
So traditional anonymization methods, like just removing names, aren't enough for this kind of complex, multi-record data.
Often they're not sufficient, or they damage the data too much. Techniques like slicing the data, K-anonymity.
Remind me what K-anonymity is.
K-anonymity ensures that each record in the released dataset is indistinguishable from at least K-1 other records based on their quasi-identifier. So you're always hidden in a crowd of at least K people.
Okay.
Then there's L-diversity, which adds a requirement that the sensitive attributes within each of those K-anonymous groups must be diverse. And T-closeness goes further, ensuring the distribution of sensitive attributes in a group is statistically similar to their distribution in the overall dataset.
Sounds complicated.
They are. And while useful for simpler datasets, These techniques can result in significant information loss, especially with high-dimensionality data with lots of attributes, or in these tricky 1M scenarios. This information loss can sometimes render the data statistically useless for the researchers, which defeats the whole purpose of sharing it in the first place.
So we need something smarter.
Exactly. To address this, a proposed ML-driven solution discussed in the source is the CBPP algorithm. It stands for an efficient algorithm for privacy-preserving data publishing of 1N microdata with multiple sensitive attributes. It specifically aims to achieve a better, more optimal balance between rigorous privacy and maintaining that crucial data utility.
Okay, CBPP. How does it actually work? What's its core mechanism to achieve that tricky balance?
The CBPP algorithm employs a clever process called anonymization.
Anatomization, like dissecting something.
Kind of. Think of it like taking a complex medical file containing all of an individual's information over time and carefully splitting it into two separate anonymized folders or tables. One table is specifically for the quasi-identifiers, those less sensitive, but potentially identifying bits like age range, generalized location, maybe admission month. The other table contains only the truly sensitive attributes, the specific diseases, the medications, the income bracket, etc., linked perhaps by an internal non-identifying key.
So you separate the potentially identifying info from the really sensitive info.
Exactly. These two tables are then processed separately. Following the separation, the quasi-identifiers are generalized. For instance, a specific birth years might be replaced by broader age ranges, like 1524, 2544, 4560. Zip codes might be similarly grouped into larger geographical areas, maybe using just the first few digits. This generalization reduces the precision of the quasi-identifiers, making re-identification incredibly difficult, even if someone tried to combine them with external public records. But it does so without completely removing their analytical value for demographic studies or trend analysis.
So researchers can still see patterns, like people in this age group, in this region, have higher rates of X, without knowing specifics about individuals.
Precisely. This clever separation and generalization allow researchers to query patterns across these generalized groups, often by joining the two tables back together, using the internal key during analysis, but without ever seeing identifiable sensitive data linked directly to easily re-identifiable quasi-identifiers for any single person.
That's a very clear way to visualize it. It sounds promising. And has this intelligent privacy-preserving approach been tested in a real-world scenario? Did it prove effective?
Yes, absolutely. The CBPP algorithm wasn't just theoretical. It was meticulously implemented in Python and rigorously tested on the real-world INFORMS dataset. This is a publicly available dataset often used for privacy research derived from survey data. It originally contained over 230,000 records, which were eventually grouped down to represent about 40,000 unique individual records, many likely having multiple entries over time, a good test for the 1M problem.
And what data did they use from it?
For the test, they chose birth year, month, sex, and race as the quasi-identifiers. And they used education year, income level, and poverty line status as the sensitive attributes they wanted to protect. The effectiveness of the privacy preservation, crucially, wasn't just assumed, it was measured by query accuracy.
Query accuracy, how does that work?
It basically gauges how much information loss occurs due to the anonymization process. Researchers run typical analytical queries on the anonymized data, like what's the average income for females aged 25-44, and compare the results to the answers they would get from the original non-anonymized data. The aim is to achieve high query accuracy, meaning the anonymized data still accurately reflects the underlying patterns and statistics of the original data, even while providing strong, measurable privacy guarantees.
So it shows the data is still useful.
Exactly. It demonstrates how ML isn't just driving incredible innovation in performance and prediction, but it's also providing these intelligent, sophisticated solutions for the really thorny ethical and practical dilemmas of data in our hyper-connected world. It helps ensure that progress doesn't necessarily have to come at the cost of fundamental personal privacy. #tag outro.
Wow. We've explored a vast and truly fascinating landscape today, from the micro level of classifying individual cells for health diagnoses, right up to the macro scale of global communication networks and predicting environmental events like floods. It's become incredibly clear that machine learning is not just another sophisticated tool in the engineer's toolkit. It's a fundamental shift, isn't it? A real paradigm change in how we approach and solve complex problems across pretty much every facet of engineering.
I agree completely.
It's unlocking solutions, providing capabilities that were once genuinely unimaginable.
Indeed. This deep dive has vividly shown, I think, how ML acts as our expert guide.
through these massive, often messy, complex data sets. It's extracting the most important insights. It's connecting seemingly disparate fields like connecting satellite data with rainfall for flood prediction. And it's enabling us to engineer solutions with unprecedented precision, foresight, and adaptability.
Hmm.
It's providing us with those advanced warnings for natural disasters, optimizing our transportation systems for enhanced safety, making our transition to electric vehicles smarter and more efficient, helping secure our digital future against new threats, and even, as we just discussed, developing sophisticated ethical frameworks to help safeguard our personal data in this world of pervasive connectivity.
It's an exciting and sometimes maybe a little daunting future that ML is helping to build.
It certainly is, both exciting and challenging.
And it leaves me with this final thought for you, our listener, something to maybe mull over. As we continue to collect more and more data from literally every aspect of our lives and from every engineered system around us, and as these ML models become ever more powerful and deeply integrated, what new, currently unimaginable applications of machine learning might become possible in the next decade or two? And perhaps more importantly, what ethical considerations must we prioritize, must we continuously revisit and debate as these intelligent systems become even more deeply intertwined with the very fabric of our society, our work, and our world?
That's the big question, isn't it?
Oh,
Where does this lead and how do we guide it responsibly?
something to think about. Until our next deep dive.